Welcome to Experiment 2, Physical Properties of Matter, Melting Points and Boiling Points, which again, like the Density Lab, can be a confirmation or at least a data point into determining the identity of an unknown. So we're going to determine the melting point of a solid using this apparatus, and we will determine the boiling point of a liquid using this apparatus. Now it's possible to do them both at once. It's a little kind of rubbing your head and patting your stomach kind of a thing. But we'll see what we can do to keep this as clear as possible.
For the boiling point of an unknown liquid, the first step is to get approximately 250 milliliters of water into a 400 milliliter beaker, or you can use a smaller beaker and get 150 milliliters of water into a 250 milliliter beaker. But I'm going to use the larger 400 milliliter beaker with 250 milliliters of water.
Go, close enough. Now this hot plate does not look whether it looks the same whether it's hot or cold, so you just got to be careful with these things. It has a spinner in it that we are not going to use. If we had a little magnet, we could drop it into this beaker and it would spin around and around and around if we needed to stir it, but we don't need to worry about that. The hot plate, though, now you might think, oh, if I just want to boil water, I'll just set it on 100 degrees Celsius. The issue is, of course, that this surface is not going to transfer at 100 degrees all the way to the water. So we're going to crank it. Now, do we need to crank it to 540 degrees? Probably not. It's going to get a little bit smelly because whatever's stuck to the top of this thing is going to start getting stinky. But we can certainly set it relatively hot. Okay? Now, we are going to put some boiling chips into our water, which is just regular old tap water. Because you can have something called superheating, which you don't go over until very, very, very late in the semester. But suffice to say, it's the same reason that you should not, and if you've ever looked at the instructions, it says you should not heat just a cup of water in the microwave. If you don't have a surface for the bubbles to start forming on when you're boiling your water, it's called a nucleation point. If you don't have a place for the bubbles to nucleate, sometimes they won't nucleate, and you can get the water much, much hotter than 100 degrees without it boiling. And then, let's say you're making tea and you dropped a tea bag in there, the whole thing would explosively overboil. Now, I told my sister-in-law this, and she didn't believe me. And so she tried it by boiling some water in the microwave, and when she threw her tea bag in, it did explosively overboil, and she ended up with third-degree burns on her legs. Because my sister-in-law can be a little bit goofy. So there we go. All right, so this is heating. And we're going to wait for this to get nice and hot. We want our water either very, very hot or boiling, because we don't know what our liquid is. And we want to boil our liquid, so we want to make sure that we have our water as hot as possible. So we're just going to leave that for the moment, heating. All right, so we're going to skip over to part 2, the melting point of an unknown solid. Now, to determine the melting point of a solid, you have to get said solid into this melting point capillary tube, which is open at this end and closed at this end. Now, you never want to put your finger over either end because it's glass and it's sharp and it'll go straight through your finger. So I'll show you a couple of ways to fill it with powder, but the most exciting way, or the most fun way, I will show you also. So I need to get an unknown solid. So I'm just going to choose one at random over here. Not that one. Not that one. It melted already. I want to choose one that's a little bit powdery, but yeah, okay. So I have unknown number 17 here. And you can see, if I pour a little bit into a piece of paper. Now, if this was not powdery, I could put that on the paper and kind of grind it with my fingers or a spatula. But I chose a powdery one just for the sake of time. And you can see that this stuff is just a white powder. Okay? So to get it into the tube, again, notice I put it cap up, so I can just replace it on here without any contamination. I'll take my capillary tube, open side, and I just kind of tap it in there. And then you can see that there's about a millimeter or two of powder, but it's in the wrong end. It's in the open end. I need it down here at the bottom in the closed end. So what you can do, if you're brave and careful, is just whack it on the table. And then it's moved to the bottom. But I understand people that are just starting, first time they've done this, might think that, oh, I'm going to snap this tube in half and it's going to go into my finger and I'm going to bleed all over the bench. That's a bad idea. So what you can do, which is also kind of fun, is have a long tube, not even in the picture, and I just take the tube and I put it in the top. I'll show you. Put the tube in the top and I drop it. And it bounces a few times, and that packs the solid down into the bottom. I can do it again, just for fun. Try and get it close. See it bounce, maybe? Boing. Oh, I had some good height. Went all the way up to off the camera. Now it's down flat. All right. And so now my solid is packed into the bottom of my capillary tube. Great. My melt temp apparatus. Let me just clean up a little bit here. Get the extra solid out into my waste bottle. Properly labeled waste bottle. Don't think I'm going to need another tube, so put those away. Clean as I go. My melt temp apparatus plugs directly in this cable into this little computer, which is made by the Vernier Corporation. It's pretty powerful in that it you can hook up a thermometer to it, which is what we're doing. You could hook up a pH meter, you could hook up a balance, you can hook up a Geiger counter. This thing has a ton of different instruments that you just plug in, and it knows what instrument's plugged in, and it just gives you the right readout. So it'll give us degrees today, but if we wanted something else, if we were measuring pH, it would give us the pH value. If we were measuring nuclear radiation, it would give us the number of counts. So it's pretty cool. And I'm just waiting for it to boot up, which is the problem with this. It is a very slow but very versatile instrument. Very slow but very versatile. While we're doing our melting temperature experiment, which takes a little while, we can go back over to our boiling experiment. So, still loading. Please wait. Hopefully it'll be ready soon. I can show you, there we go, and when I plug in my temperature sensor, it knows that there's a temperature sensor, and it's reading room temperature, which is around 25 degrees, 24.8, if we read it exactly off of here, which we should. Now, the melt temp apparatus is going to be a little bit challenging to show you, but I can try. You will look through this window, which has a magnifying glass in it. And you can see there are 3 little slots looking through that magnifying glass where I could put my tube. And so, let's get my aim. There it is, going into slot 1. See? So I could do 3 different ones at once if I wanted to. Can't really aim without looking. There we go. There's going into slot 2. Seems to be a little broke. There's a tube broken off in it. Can't use that slot. And there's the 3rd slot over there. So you can do 3 different melting experiments at once. Now the challenge with melting is you're looking at this small thing through this magnifying glass. You turn on the temperature, which puts a little light on it, makes it a little bit easier to see. And you have to watch for the first drop of liquid being formed to the last bit of solid disappearing. You're always going to measure a melting point range. A melting point range. And so what's really nice is the old school way, you stuck a thermometer here in the top and you had to read it off analog, but now it just hooks up to the digital readout. And this thing has a set temperature on it. So I don't know what it's an unknown, so I don't know what it melts at. I'm going to set it at 140. The challenge is that I have to have it melt, that first drop of liquid to last drop of solid. That range has to occur at 1 to 2 degrees per minute only. If it's going faster than that, the temperature readout isn't quite catching up with what's going on in the melt temp. And so it's giving you imprecise data, and we're all about precision. Now you can see my water is starting to boil here, so I'm going to crank this back down to only maybe 250 or so, because I don't need to evaporate all my water. So now while this is warming, I'm going to keep one eye on it and look for any liquid forming. I'm going to switch over to my unknown liquid because it is ridiculously a fast experiment. All right, so I have a temperature probe. This one just plugged into the vernier instrument straight with its own cable. This, I'm going to measure the temperature of what's going on in there, just for curiosity's sake. Right? So I'm going to plug my temperature probe into meter, and you can see now it has two different temperatures on it. The blue one, the bottom one, 28.5 currently, is the one that I just did. Now, I don't want to melt my cable, so I'm going to be really careful and not let it touch. And I should be somewhere near 100 degrees, so let's find out. Okay, my boiling chips worked. I don't have any issues with explosive overboiling. So my water today is doing something impossible. It is boiling under 100 degrees. We'll give it a minute to catch up. Now my temperature probe also, the cable shouldn't touch the hot plate, and also technically the probe shouldn't touch the bottom. This is a good way of determining, is our temperature probe properly calibrated? It should be exactly 100 degrees. Clearly, it isn't. Water can never boil lower than 100 degrees. Contamination, as we'll see in a different lab later in the semester, raises boiling points and lowers melting points. Pure compounds melt at a very defined temperature range and boil at a very defined temperature. Contaminated liquids boil at a higher temperature. Contaminated solids melt at a lower temperature and a wider temperature range. So just seeing how hot the water is for curiosity's sake, and it looks like our temperature probe may be a degree or two off, which is very useful to know if we have trouble identifying our unknown liquid. Turn this back up because it stopped boiling so much. I'm going to put on 300. All right, I'm going to grab an unknown liquid. Here we go. Unknown liquid number 24. Again, there's a whole bunch of sample data provided that your instructor will give you. I have a test tube to put it in. I have a 2-hole stopper. That's very important that it's got 2 holes in it. Because if I put my liquid in the test tube, which I will, about an inch of liquid in the test tube, okay, stopper it, put in my temperature probe. Now if this was only 1 hole, that would be a sealed test tube, aka a pressure vessel. And when liquid turns to gas, it massively expands. If this was water in this test tube, which it isn't, if this was water in the test tube, 18 grams of water would expand to 22.4 liters of steam. This test tube is nowhere near 22 liters. 18 grams of water, 18 milliliters of water, about here. So massive, massive expansion. If this hole was sealed in the top, this test tube would explode. So you must keep your second hole open. All right, my boiling has slowed significantly, but it shouldn't matter. Right? If I carefully, again, smell this liquid, wafting it to my face, to me, it smells like something out of my medicine cabinet at home. Not nail polish remover. Something out of that medicine cabinet at home. Doesn't smell like something I should be drinking. Alright, I'm going to carefully get the cables so they don't melt. Submerged my liquid down in... Oh, I forgot an important step. Did we not read it? Boiling chips in our unknown liquid. Very important that we did that. We do not want to explosively overboil our liquid. So we'll add a couple of 3 boiling chips to our liquid. Now we'll carefully stopper it. Carefully clamp it. Jed Clampett of the Beverly Hillbillies. I am putting references in this video that are way too old. And then my goal is to get this submerged down there as deeply as possible. Not really touching the bottom. Don't want that. And we should soon see... Let's switch this forward. Our liquid in the test tube is boiling. Now it might be a little bit challenging to see because the water outside the tube is also boiling. Yeah, I don't think I can get it any closer. But the liquid in that test tube is definitely boiling. And if we look at our blue temperature, the bottom one, because that's the liquid, the red one is the unknown solid, which is still a white powder. No change. I am boiling my liquid, and it is at 79.9, 80, 80.2. Now, notice the temperature probe is in the middle of the test tube. It's not touching the sides of the test tube, but it's also not touching the liquid. It doesn't matter. You haven't gotten to this in class yet, but when a liquid boils, the gas over it is the same temperature as the boiling liquid. So I can be confident, even though the probe isn't touching the liquid, that that liquid is at 81.3, and that's where it's staying. 81.3 is my boiling point of my unknown liquid, not changing. It's just coincidence that the solid in the melt temp is the same, roughly the same temperature. But 81.3, blue one, bottom one is my my boiling point of my liquid. All right, that's it. That's it for the boiling point of the liquid. It's a super, super fast experiment. You've got the liquid boiling, you can see it there boiling, and we measured the temperature over it, and it was 81.3. Okay, it's still reading 81.3 on the temperature probe. All right, so we're done with our unknown liquid. Okay, I can wait for this tube to cool a little bit. I can take my temperature probe out, don't need it anymore, and I can certainly unplug the temperature probe from the vernier computer and set it aside. Now I just have to be careful because this hot plate is going to be hot. Even if I turn it off, this hot plate is going to be hot for quite some time, and as is the liquid that's in it. All right, so I'm just going to be very careful. Move these things out of the way so that I can hopefully show you the solid melting. Very careful. Boiling water all over yourself is generally a bad thing. Our solid is at 89.6 and nothing has happened. Let's see if I can show it to you in here. You look in there, try and get it where the light is not blinding the camera. See, there's where to put the tube in. This might be impossible. Up there, we had it for a second. The glare, the glare. Jeez, there we go. Here's the tube. Still, sorry, a white powder. Nothing has happened to it yet. So we're waiting. We are waiting, and awaiting, and awaiting. And we will watch it. The temperature is now at 95.8, 0.9, 96. So this is rising much too rapidly for a good melting point experiment if it were to melt now. Now I have it set where it's going to expectedly melt at around 140. If I flip back to table 2.2 and look at the potential solids for this experiment, I've got one that melts at 48, one at 54, 59, 71, 82, 114, and 122. Well, we are already at 98. So it's definitely not the one that melts at 48, 54, 59, 71, or 82. Naturally, I chose a high melting one. Annoying. Okay? But it can't be any of those because, remember, contaminated solids melt at lower and wider temperatures. And so I'm hoping maybe it's at the 114. So I'm actually going to turn this down because I don't want it to rise so quickly. Right? Because if it melts at 114, I want it to rise only a degree or two per minute at 114. So this could take a little bit of time, and we'll just edit it out. But I want to look for the start of solid becoming liquid, and I want to look for the last bit of solid melting. Notice that my temperature rise is slowing down now, which is not a bad thing. You have to have patience in the chemistry lab sometimes. So for this to get from 102 to 114 should take 6 to 12 minutes. Some people get very impatient and frustrated, and so they just crank the temperature up. And then temperature rises really rapidly, and they say, oh, it melted from 118 to 147. Like, well, how long did that take? 118 to 147 is almost 30 degrees. Did that take 30 minutes for it to melt? No, it only took a minute and a half. Well, no wonder you got a crazy temperature that's nowhere on our list. Because you did it much, much, much too quickly. So, we had our boiling temperature. We could look at table 2.1 and determine a likely identity of our unknown liquid. And hopefully soon we will see some change here in our solid, and it will be the one that melts at 114, not the one that melts at 122, but we shall see. So far, nothing. Notice that our temperature is increasing much more gradually now, which again is a good thing. I want to see first drop of liquid to last bit of solid, that temperature range. The thermometer digital readout has a tenths place on it, so your data sheet should absolutely have a tenths place on it. Still nothing, as expected. It's either going to be at 114 or at 122. Again, I'll show you, if I can, what's going on in the mel temp. Here's our solid. Sometimes helps to rotate the tube and jiggle it a little bit. Still solid. No change whatsoever. You have to watch out. The top part of the melt temp up here gets very, very hot. If, let's say, we went too fast and we missed our melting point, what we could do is turn our knob down into the blue section where there's a little fan. We can watch it cool, because the freezing temperature as the solid cools and the melting temperature as the solid is heated. Same thing. Same temperature. We could watch it cool if we missed it melt. But we're not going to miss it. We're watching, we're at 108. So hopefully we're only 6 degrees away. But if we hit 114 and nothing's happened, then we'll have to crank it. Or wait, actually, another 8 minutes or 6 minutes or so, 8 minutes, and until it gets 122. Patience. Patience. Still nothing. Our solid is exactly the same as it was. Our boiling hot water is now cool enough for me to hold and dispose of properly by putting it back to the sink that it came from. My hot plate is still very hot. In fact, there's a warning light on it that tells me that it's hot. But I definitely do not want to touch that, especially with my glove, because it might melt the glove to my hand. We are at 110. Still no change. Very, very slightly increase my temperature. Solid. No change. $111. Is the suspense killing you? It's either going to start melting in 3 degrees or nothing is going to happen until 122. But I tell you what, if it doesn't melt before 114, we're going to know that it's the 122 because it's nice. We don't know what our unknown solid is, but we know it's something on this list, which is kind of convenient because it has to be the hottest one if it doesn't melt at 114. I suppose you could try and waft the odor of the solid to your nose and see if you could smell anything out of the bottle, not out of the tube. That'd be dangerous to put the glass tube near your face. But a lot of solids don't have any odor. Some of them do, so you could very, very carefully try that. But you definitely don't want to be snorting white powder. That'd be bad. We're at 113.2, and we have absolutely no change. 113.5. Oh, wait a minute. I see liquid. Liquid has started to form, so I'm going to write down 113.5 as my starting melting point range. And remember, contaminated solids melt at slightly lower temperatures, so that might actually be indicative of a slight contamination. Yeah, we're at 114.3. It's still a little bit of solid left. I still see solid, but I also see liquid. Now, sometimes the solid tends to shift around in the tube. That doesn't count. This is definitely solid becoming liquid. It's not a reaction. It's just a physical change. Still a little bit of solid left. We're at 114.9. And there's still a little bit of solid. 115.1. Remember, a wide temperature range is also indicative of a contaminated solid, so there might be some minor contamination here. These bottles might have been used many times. The student that used it before me might have accidentally contaminated it with something. And the last bit of solid is gone now at 115.9. Try and let you see it. It may not show you that well in here. Get it really, really darkened. Now, come on. No solid left. It's just liquid in that tube now. Now again, if I had gone too fast or I had missed it, what I could do is put my melt temp down into cooling mode. Blue light is on. There's a little fan here on the side that kicked on. And I could watch as my temperature now is starting to drop. And I could watch the solid form, because melting and freezing are the same thing, just whether the energy is being supplied to the solid or to the liquid. Or from the liquid, I should say. Okay? But I don't really want to watch this freeze. Although it is at 111 now, cooled very quickly. And I am not seeing solid formation, but sometimes that can be very challenging because the tube is so narrow. It can just be one big hunk that looks nice and clear and colorless rather than white again. But that's the end. We've determined our unknown liquids boiling point. We have determined our unknown solids melting point range. And from those two, either the data that I just supplied or the sample data that your instructor supplies, you can determine your likely unknowns or your probable unknowns identities.